right. Good morning, ladies and gentlemen. Today is
Tuesday.
Monday. Okay, Monday, October 8th. Okay, so today we're going to do optimizing, and you can't even see that right now, optimization with linear programming. Okay, now you have solved systems of linear equations by graphing, right? And when you solve a system of linear inequalities, I said equations, I meant inequalities, what do you have to do? Always. Inequalities.
Shade.
Shade. Oh, your guys are brilliant. Okay, so we're going to find the maximum minimum values of a function over a region and solve real-world optimization problems using linear programming. Okay, so now they're giving you an example right here. And it says, an electronics company produces digital audio players and phones. A sign on the company bulletin board is shown, and that's down here. Now, if at least 20 or 2,000 items must be produced per shift, how many of each type should be made to minimize the cost? Okay, so when we're going to come up with a minimization function, and we want to know how much of each item that your company is making should you make to minimize the cost. And then we also can have a graph or an equation that we would need to plug in points to see what would be the maximum profit, right? Because that's the whole point, is to maximize your profit. So we would have to take in the cost consideration and the income. And then, income minus the cost leaves you with profit. Okay. The company is experiencing limitations or constraints on production caused by customer demand, shipping, and the productivity of their factory. A system of inequalities can be used to represent these constraints. Okay, so then we have these constraints right here. Now, we have the audio and we have the phone. The minimum number that they need to make for the audio is 600 and phone 800. So that gives us a constraint right there. The maximum they can make for audio is 1,500 and 1,700 for phone. And then they have the cost of $55 and $95. And so we're going to put all of those into a graph and then see where our what's called feasible region is. Yep. Okay. All right, so here we go, and we've looked over at, let's look at the vocab real quick. Linear programming, feasible region, that's the area that's shaded. We'll talk more about that. Bounded, unbounded, and optimized. Okay. Now, maximum and minimum values. Situations often occur in business in which a company hopes to either maximize profits or minimize costs, and many constraints need to be considered. And in reality, more than the ones they're going to give you. If you actually had your own business, you would have to think about a lot of things, but they're saying they put it all together in the equations that they're going to give you. Okay. So linear programming is a method to find the maximum or minimum values of a function over a given system of inequalities, with each inequality representing a constraint. After the system is graphed and the vertices of the solution is set, this is called the feasible region. And we substitute and are substituted into the function. So the vertices of the corners, okay? And by that you can figure out your maximum or minimum value of whatever kind of function you have. If it's a profit function, cost function, or whatever. Now, obviously, you would want to maximize a profit function, right? And obviously, you would want to minimize a cost function. Okay, so here's a couple of drawings of them. Here's the constraints, right? And if you guys remember, when you're graphing these, that's a boundary. Now, when we're talking about a situation that is a scenario of a business or whatever, then we call that constraints. Now, a feasible region is enclosed or bounded by the constraints. The maximum and minimum values of the related function always occurs at a vertex. So you don't have to worry about plugging in any of the points on the inside. although they work, they would make the statement true, or all of the statements true, they would not maximize or minimize your function that you're trying to maximize or minimize, okay? All right, now you have, look at this one, and this one is called, this feasible region, the shaded area, is called unbounded. Can anybody guess why? And you have talked about this in Algebra 1, but you've slept a minute or two from then. So why do you think that's called unbounded? Ben?
It's going on infinitely.
It's going on infinitely, in this case, downward. These two lines are parallel to each other, so they're never going to cross, right? So you have this, you have these two these two vertices that you can use, but then you've got to think about this area right there. All right. And unbounded regions either have a maximum or a minimum value. They can't have both. Now, bounded regions, so this feasible region here, which is bounded, it will have maximum, minimum, they will have both maximum, minimum values. And they will, each one will be at that. So to find that, what we're going to talk about in a minute is, we're going to talk about it right now. You're going to take that function, either the profit function or the cost function in these cases, and we're going to put in the x's and the y's so that you put in an x, and so your maximum or minimum value is going to be whatever you get out for the y, okay? And let's talk about that more in uno momento. Now, I'm going to kind of go fast over this because I feel like you probably remember this pretty well as far as graphing an equation, okay? Now, however, let's look at this really quickly. And the notation, let me see if I can get that a little bit more focused. The notation f of x, y is used to represent a function with two variables, x and y. And it's read f of x and y. Okay. So here's an example. Now this isn't technically a scenario yet of a story problem, but it's just, you know, inequalities. Graph the system of inequalities and name the coordinates of the vertices of the feasible region. Find the maximum minimum values of the function for this region. Okay, so we want to graph all of these and then use this function. Now they're not telling if it's a profit or, now this is just a function. It's not profit or loss or, you know, income or anything. It's just a function. Okay, so we have 3 is less than or equal to y, which is less than or equal to 6. Do you see that right here we have a line that represents x equals y, y equals 6. You guys see that? Okay. Now, and it's less, y is less than 6, so that'd be shaded downward. This one is 3 is less than or equal to y, which if we read that with the y first, it would be y is greater than or equal to 3. Do you see that? Okay, so here's your 3 right here, and it would be shaded upward because the y is greater than the 3. So the region would be shaded in this middle of these two parallel lines. But now we have 2 more constraints to worry about. Y is less than or equal to 3x plus 12, right? Okay, so how do we graph y? Let's graph the related function, y equals 3x plus 12. Somebody remind me how to graph that. Who wants to do it? We have to hurry, we only have 20 minutes. Okay, thank you, Riley, go ahead.
There's a point at 12 where it crosses the line, and it goes
Okay.
3 over 1, and it is on...
Oh, you mean up 3 over 1?
Oh, sorry, yeah, down, sorry, yeah. And then the shaded line will be on the right side.
Well, it will be on the right because this line right here, it's hard to see it because it doesn't show you the 12 is way up here. So it'd be up here and you go up 3 over 1, up 3 over 1, way out there. So you could plot some points if you know, you didn't have it in your box, but he's right. That's the line right there. And it is shaded to the right because it is slanted to the right, and it says y is less than. So it'd be everything that's below it. So even though it's, or you could pick 0, 0 and plug it in and see which side to shade. And 0 does work, so it would be this side. Okay, Now, and we could graph this one. Grant, go ahead and tell me how to graph y is less than or equal to negative 2x plus 6.
It would cross the y-axis at 6 and then be going down to over 1.
Down to over 1, voila, and shaded to the left, okay? Because this one's less than, so the lower side would be the less than side, or you could choose 0, 0, plug it in, see if it works. Okay, so then all of the area that's shaded for all of them together is your, what are we calling that? The what region? Feasible region. Okay, now we're going to evaluate the function at each vertex. So we're going to plug in every x, so negative 2, right here is negative 2, 6. 0, 6, right there. Negative 3, 3, right there. And 1.5, 3, right there. Now, if you can't see nicely where those cross, what is the way that you could find out where they cross, where two lines cross? Where could you figure that out if it's not at a nice intersection of integers? You guys remember what we've done before? A system of equations. So solving a system of two equations, you just use the two equations of where that's crossing and either use what or what? Substitution or elimination, that's right. Okay, good. Now, and you could do that at every corner if need be. Or you could put it in your calculator and find the intersection too. Okay? So now, as you find out, you're putting those, here's the function, 4x minus 2y, there you go. F of x and y equals 4x minus 2y. So you're going to put your x values in there and see what your y values come out right here. So what is our minimum value? Negative 20. So at negative 2, 6, it gives us negative 20. That's the minimum value. What's our maximum value? 0. That's right, right there. And we got that at what point? 1.53. That is correct. Okay. We're going to come back and do an example after we get through the teaching part. But okay. So now, watch out, it says, before we look at example 2. Do not assume that there is no maximum if the feasible region is unbounded above the vertices. Test points are needed to determine if there is a minimum or a maximum. Okay, so if your unbounded region is going downward, you can't not assume that you have a maximum point, even though it's going to kind of look like it. And many times you will. And you cannot assume if your unbounded region is going upward that you're going to have a minimum point. Do you see what I'm saying? It's weird. It just depends on what the equation that you're trying to maximize and minimize is. And let's look at that. Okay, so do you guys feel good about being able to graph the lines? I feel like you should know that pretty well. Okay, so now we're going to, an unbounded region, graph the system of inequalities and name the coordinates of the vertices of the feasible region. So we've got to name those points. Find the maximum and minimum values of the function for this region. Okay, so we have 2y plus 3x is greater than or equal to negative 12. And you can either find the x and y intercepts and then graph it that way, or you can put it into y equals mx plus b. I don't care. However you want to get it graphed, graph it, okay? And then make sure you shade the correct side. I think you guys are good at that. So if we notice this, we have two, and you can see it right here, two slopes that are the same. So immediately we're going to know we're going to have two parallel lines, right? Okay, so right here, and they've graphed it, shaded the correct area. I believe you're good at that, so we're going to move on. Right here, this area is our unbounded region because it has no bound this way. Now, it says evaluate the function at each vertice. So negative 4, 0 is negative 36, right? And 0, negative 6 is 36. Okay, so it says the maximum value is 36 at 0, negative 6. There is no minimum value. Notice that another point in the feasible region, they chose 0, 8. It would be shaded, right? Because it would go right straight up here at 8, yields a value of negative 48, which is less than negative 36. Okay? So at negative 40, we have a maximum value of negative 30. I'm sorry, I said that wrong. At 0, negative 6, there's a maximum value of 36. But even though this is negative 36, you need to choose a point that's in the shaded region. So then you know if that point is going to give you a lower or higher, and then you can decide about the maximum minimum situation. Okay? All right. We will come back to that as soon as we're finished with the 20 minutes and do a problem like that. Okay. And I think it's going to pop up on the screen that it's going to stop recording. So when it does, if I'm not looking at it at the moment, somebody wave me down. Okay. Now, optimization. Okay, so we're going to use these feasible regions and do what I was talking about earlier and talk about an actual scenario of a business or life or whatever and see what, if we want to maximize profit or minimize cost or whatever. Okay, to optimize means to seek the best price or amount to minimize costs or maximize profits. This is often obtained with the use of linear programming. So this would be nice to have on a card, maybe with an example, so you can refer to it back easily. Okay, so we have, we're going to define the variables. That's always important. If they give you just a story problem, you need to define your variables before you start writing an equation. Write a system of inequalities that goes with your boundaries or what's needed to bound up the feasible region. Okay, then graph the system of inequalities that you've written. Find the coordinates of the vertices of the feasible region. So you might have to use a system of equations to find those. And 5, write a linear function to be maximized or minimized. Okay, now you're going to substitute the coordinates of the vertices into the function. And then you're going to select the greatest or least result and then answer the problem. So it depends on what you're trying to find if you want the greatest or the least. Okay. All right. When using a system of inequalities to describe constraints in real-world problems, often only whole number solutions will make sense. Okay. Because, like, if you're wanting to know how many phones and how many MP3 players to make, whatever, excuse me, you can't make a half a phone or a half of an MP3 player or any portion thereof. So we have to talk about whole. Now, we'll get to this in a minute, but say it said the maximum thing that you could make was 299.9. How many, whatever I just said, can you make? 299. Even though it's closer to 300, you can't just shove it in just because you want it to be. You can only make it go round down. Okay. Now, let's look at this situation right here. Refer to the application at the beginning of the lesson. Determine how many of each type of device should be made per shift. Okay. Now, if we look back at the lesson, at the beginning of the lesson, right here, we had some, let's see, that looks a little bit better. We had we have the audio and the phone. So we're going to have to identify our X and Y. In this case, would it matter which one is going to be your X and which one's going to be your Y? It will not, because one is not causing the other to happen. We don't have an explanatory variable and a response variable, right?